Hi, this is Cindy Schwartz from Vassar College. Today we're going to work on a circular motion problem. In the past, you probably had some experience with what we call uniform circular motion, which is not what we're going to do today. And that is when an object moves in a circle at a constant speed. What you're going to need to remember in order to do this new problem is that when an object does move in a circle at a constant speed, it has an acceleration, and that acceleration is pointed toward the center of the circle. Its value is equal to the instantaneous value of the velocity divided by the radius of the circle. And it points directly inward. Okay, with that being said, the problem that we're going to take on today is going to involve a toy car. Okay, so in this problem we have a toy car that moves in a circle of radius 0.5 meters. So I'll do my best to draw a circle here. And the radius is 0.5 meters, and I'm going to label that as R. I'm going to start the car over here, and it travels around the circle, and what we want to know is what is the angle between the acceleration vector and the velocity of the car when the car has traveled one-third of the way around. Okay, so take a minute and think about the question here. And now we're going to put down what we know and what we have done. Okay, so the first thing that we have to figure out is where is the car when it's traveled one-third of the way around? And this would be a good time to review the unit circle material if you are not clear that one-third of the way around is equal to 2 pi over 3 radians. And that brings us somewhere around here. So this is our final position. So we're going to have a final velocity there, and we'll have an initial velocity here. Okay, so for the linear part, in order to figure out the final velocity, we have to figure out what distance did it travel. So we're going to go back to some of the relationships that hopefully you learned at some point but may have forgotten. So I've redrawn the picture here, and I've labeled some new quantities. S is the length of the arc that the car travels in, and theta is the angle subtended by that arc. So one of the formulas that we should be familiar with is the relationship between that arc length and the radius r. It's important when we use this equation that theta must be in radians. Okay, so S is equal to the radius which we were given of the circle, which was 0.5 meters. And the angle was 2 pi over 3. So that gives us a value for S of pi over 3, which is approximately equal to 1.047 meters. Okay, so now we're going to go back to our kinematics to figure out the distance s. So we're going to use v final squared is v0 squared plus 2a, and instead of x or y, because I'm dealing with s, I'm going to use s final minus s0. And I'm going to take my s0 to be 0. Okay, so when we pop our numbers in there, we'll do v final squared equals, it starts with an initial velocity of 0. The acceleration we were given is 0.2, and s final was pi over 3 meters. Do our calculation there, and we get v final squared, and I'm going to keep it as squared, you'll see why in a minute, is equal to 0.42 meters squared per second squared. Now we have to go back and realize that at that point, I'm going to draw the velocity vector, v, and so this is the v final that we just found. And if we do take the square root of that number, we will get about 0.65. Okay. Now to calculate the acceleration, we remember that we do have a centripetal acceleration, and the formula for that is a sub c is v final squared over r. That's why I kept this v final squared, 0.42, divided by the radius, which was 0.5 meters, gives us an acceleration of 0.84 meters per second squared. And remember that points radially inward, so I'm going to put that on there in green. Okay, so that's the green vector. Now, you might say, okay, well, that's it. But the thing is, we do have a linear acceleration, that is an acceleration in the direction of v final, which we usually call the tangential acceleration. So I'm going to put that in blue also. So we have AT is equal to, and we were given a number for that, 0.2 meters per second squared. So the vector A has two components, a tangential component and a radial component. I'm also going to put this one in green as well. Okay. And now we need to find the resultant vector for that. And that's not too hard to do, but we're going to do it on another page. Okay, so this is the point that we're considering. And remember, this is V. Okay. And then we have two components for A. We have an inward component of about 0.84, and we have a tangential component of 0.2. So we can find the resultant vector, which I'm going to draw. So this is A total. And to find the angle between V and A, at this point, we need to do some trig. So I'll mark the angle, theta, and theta is equal to inverse tangent of 0.84 over 0.2. And from that, when we put that in our calculator, we get an angle of about 76.6 degrees. Okay. So as we can see, the acceleration no longer points directly inward, and in fact, as this object keeps accelerating round and round and round the circle, you may want to think about what happens to the direction of that total acceleration.